Hello students, welcome to my channel Engineers Academy. Let's solve this one another problem. In this problem it is said that determine the reactions at A and B for the beam subjected to a combination of distributed and point loads. So now we have this beam which is supported at this point A and B, and it is subjected to distributed load and the concentrated load. And the concentrated load is 1.5 kilonewton and it is making 30 degree with the vertical. So now this particular problem can be solved by using two methods, you people can say, right? So I am solving this by using those two methods, and we will compare those two methods, right? So in the first method, what we will do is that we will divide this area which is associated with the distributed load into two triangles, right? So let's say that we have two triangles. We have this triangle. Let's say that this is area 1 and this is, let's say, area 2, right? So if we want to find the resultant of this area 1 distributed load, so then that is, let's say, R1. That concentrated resultant of this area 1 will be equal to half the area of this area 1, right? So this will be equal to half base. So the base of this triangle is 1.2 plus 0.6, so this is 1.8, and the height of this triangle is 2 kilonewton per meter, right? So this is 2. So this 2 will cancel out, so this means that R1 will be equal to 1.8 kilonewton, right? Similarly, we can find that R2 as well, right? So R2 will be equal to, again, this area 2, so that is half base, so base is 1.2 and the height is 2, so this will cancel out, so this means that R2 is equal to 1.2 kilonewton. Now the next thing is that we have to determine the location of this R1 and R2, and let's say that we want to find the location of this R1 and R2 from this end. Let me represent my origin, right? So let's say that if this is my positive x and y axis, this is my positive x and this is my positive y, and my origin is located here, right? So if let's say that the centroid of this area 1 is located somewhere here, right? So let's say that this distance is, let's say, x1, let's say this is, let's say, x1, and let's say that the centroid of this area 2 is located somewhere here, let's say. So let's say that this distance is, let's say, x2. This is x2. Let me write it in black, right? So this is x2. So now x1, as we know that the centroid of a triangular area is located at a distance of 2/3 from this apex, right? So we can say that this x1 will be equal to 2/3 of this base, right? So this is 1.2 into 0.6, so this is 1.8, right? So this will give us 1.2 meters. And similarly, if we want to find this x2, so then this x2 will be equal to this 1.8, right, plus this distance, this small distance, this distance. So this distance will be equal to 1/3 of this base, right? Since from the apex, from this point, this distance will be 2/3 of this 1.2, and from this base this is 1/3 of this 1.2, right? So we can say that this is 1.8 plus 1/3 of that base, which is 1.2, right? So this will give us 1.8 plus 1 divided by 3 into 1.2, so this is 2.2 meters, right? So now we can replace these two concentrated loads, which are represented by these two areas, area 1 and area 2, by R1 and R2, and the locations of R1 from that origin is 1.2 meters and the location of that R2 from that origin is 2.2 meters. So now let me replace these distributed loads by these R1 and R2. So we can draw that R1 here. That R1 will be, the line of action of this R1 will be passing through this centroid like this, and this distance is, since this distance is 1.2, so this means that this R1 is passing through this point A, since point A is at a location of 1.2, right? So this is that R1, which is equal to 1.8 kilonewton, and similarly that R2, which is 1.2 kilonewton, is passing through this centroid, and this centroid is at a distance of 2.2 meters from this end of this beam. So this is that R2. Which is equal to 1.2 kilonewton, right? And similarly we have this concentrated load here at this point, right, and it is making 30 degrees. So now if I isolate this beam, so we will have a free body diagram, and let me draw that beam as well. This will be our beam. So now we can isolate our free body diagram. So this will be our free body diagram. So now if we look into this beam, so here we will have that at this point A, we will have a X reaction like this, and we will have a Y reaction which will be acting vertically upward in the positive Y direction. So now if we apply the summation of moment about point A equals to 0, so now as we can see that this R1 is passing through this point A, and these reactions AX and AY are passing through this point A, so they will not produce the moment about this point A. R2 is producing the moment about that point A. So I will write R2, and R2 magnitude is 1.2, so I will write 1.2, and the perpendicular distance of this 1.2 kilonewton force from this point A is how much? So this x2, this whole distance is 2.2, and point A is at a distance of 1.2, so 2.2 minus 1.2. So the distance of this R2 from this point A is 1 meter, so I multiply this with 1, right? And similarly this 1.5 kilonewton force is making 30 degrees with the vertical, so we can resolve this into its components, right? So it will have one component will be acting in this direction, this one will be the cos component, and it will have one another component will be acting in this direction. This one is the sine component. We can write that this is 1.5 cos of 30 degrees, and this is 1.5 sine of 30 degrees, right? So now as we can see that this cos component is producing the clockwise moment about that point A as well, right? So I will write minus, and this is also producing the clockwise moment about that point A, so I will write minus with it as well, right? So this is 1.5 cos of 30 degrees, and the perpendicular distance of this cos component from that point A is the summation of 1.8, 1.2 and 0.6, right? So we will write this 1.2 and 0.6 is 1.8, so 1.8 plus 1.8, right? So this is 2 times 1.8, or we can say 1.8 plus 1.8, right? And similarly here at this point B, we will have RB reaction as well, right? So here we will have that RB, right? So now as we can see that this RB is producing the counterclockwise moment about that point A, so I will write plus RB, and the perpendicular distance of this RB from that point A is the summation of all these, right? So this is 1.8 plus 1.8 plus 1.2, and this will be equal to 0. So this equation will give us that RB reaction, the reaction at this roller support, right? So we can simplify this. So this is, so these two terms equals to minus 5.88 and plus RB. So we have to find this RB. This 1.8 plus 1.8 plus 1.2. this is 4.8, right? So 4.8 RB, and this is equal to 0, or we can say that 4.8 RB equals to 5.88. So RB equals to, so this is 5.88 divided by that 4.8. So 5.88 divided by 4.8. So this is equal to 1.225 kilonewton, right? So 1.225 kilonewton, right? So this is that reaction at point B. Similarly, if we apply the summation of forces along y equals to 0, so as we can see that this AY is acting in the positive y direction, so I will write AY. This R1 is acting in the negative y direction, and R1 magnitude is 1.8. This R2 is acting in the negative y direction, so it is 1.2. This cos component is acting in the negative y, so I will write minus 1.5 cos of 30. And this RB is acting in the positive y direction, so I will write plus, and RB magnitude is 1.225. So this will be equal to 0, or we can say that AY is equal to the summation of all of these. And the sign of 1.225 will become negative, right? So this is minus. So this is 1.8 plus 1.2 plus 1.5 cos of 30 minus 1.225. So this is equal to 3.07 kilonewtons. So AY equals to 3.07 kilonewtons. Now this is one method of solving this particular problem. The second method is that we find the centroid of this whole area, right? So, and then we locate the resultant of this load which will pass through that only one centroid of this only one area, right? And then we will solve the problem by summation of the moment about that point A and the summation of forces, so applying the equilibrium condition, right? So now how we find the combined centroid, or how we find the centroid of this whole area? So that is very simple, right? So how to find that? So let me clear this area first. So then the only one centroid, let's say that the centroid of this area is located somewhere here, let's say. So then let's say that x bar is the distance of this centroid from this end of this beam. Let's say this is x bar. So then this x bar will be equal to x bar multiplied by the total resultant of this distributed load, and that will be equal to the summation of x1 into area 1 plus x2 of area 2, right? So this will give us the total the only one centroid of this whole area, right? So we can simplify this equation. We can write that this x bar into r will be equal to the summation of xn an, right? And this r is the resultant of this whole distributed load, right? So if we have two areas, then we will find this x1 a1 plus x2 a2, right? So then what is x1? We have already determined that x1, right? So this is 1.2, and area 1 is this r1, right? So we can multiply it by 1.8, right? Plus x2. So x2 is 2.2, and area 2 is this 1.2. So I will multiply this with 1.2, and x bar into r, and r is this whole area, right? So we can find this whole area, since it's a triangular area, so we can write that this is half base. So the base of this whole triangle is 1.2 plus 1.6 plus 1.2. So we can write that this is 1.2 plus 0.6 plus 1.2, and the height of this triangle. So the height of this triangle is 2 kilonewton per meter. So I will multiply this with 2. So this will cancel out, right? So this gives us 1.2 plus 1.2, 1.2 plus 1.2 plus 0.6. So this is 3 kilonewton. Right? So then if you want to find this x bar, so then we have to divide this whole sum by this r, which is 3 kilonewton, right? So we will divide it by that R, and R is equal to 3 kilonewton. So this will give us the centroid of this whole area, right? So this is 1.2 into 1.8 plus 2.2 into 1.2 divided by 3. So that is equal to 1.6 meters. Right. So now we can modify this free body diagram, right? So this means that the resultant R, which is 3 kilonewton, is located at a distance of 1.6 meters from that end A. From this end, right? So let me replace that. Let me remove all these. So this means that total resultant is acting somewhere here, and this distance is 1.6 meters, right? So now again, if we apply the summation of moment about point A equals to 0, so we will get that same answer, right? So the summation of moment about point A equals to 0. So now as we can see that this is that 3 kilonewton force. So as we can see that this 3 kilonewton force is producing the clockwise moment about that point A, and the perpendicular distance of this 3 kilonewton force from this point A is how much? So this whole distance is 1.6, and A is at a distance of 1.2. So 1.6 minus 1.2 is 0.4, right? So this is 0.4, and it is producing clockwise moment, so this is minus. Similarly, this cos component is producing the clockwise moment about that point A, so I will write minus 1.5 cos of 30, and the perpendicular distance of this cos component from that point A is the summation of 0.6, 1.2 and 1.8. So this is 2 times 1.8, and similarly this RB is producing the counterclockwise moment about that point A, so I will write plus RB, and the perpendicular distance of this RB from that point A is 0.6 plus 1.2 plus 1.8 and plus 1.2, right? So I will write this 0.6 plus 1.2 is 1.8, and 1.8 plus 1.8 is 3.6. So 3.6 plus 1.2, and this will be equal to 0. So this will give us that same RB, right? So let me calculate it. So minus 3 into 0.4 minus 1.5 cos of 30 into 2 multiplied by 1.8. So this gives us minus 5.88 equals to plus RB, and this is 4.8 equals to 0. So from this we can write that 4.8 RB equals to 5.88, and RB equals to 5.88 divided by 4.8. So this is again RB equals to 1.225 kilonewton. So I hope you people would have understood this second method as well, right? So in the second method we determined the centroid of this whole area by applying this equation, and this is that centroid equation, right? This is that the summation of the moments of all the areas about a particular point, and this is the moment of that resultant force, right? So this is that principle of moment equation, right? So now it's up to you people that either you people want to replace the distributed loads by their respective resultants, or you people want to replace the distributed load by only one resultant, right? But both the methods will give us that same answer. Kindly subscribe my channel if you haven't subscribed my channel yet, and like this particular video if you people want me to solve such more problems.